All right, hey guys, this is my Physics 2212 Lab 6. So, introduction about this lab. So, the purpose is to investigate magnetic induction and currents by analyzing how a falling bar magnet interacts with an aluminum tube and comparing the observations to computational models. And so, we got the following results. So, the experiment time is 1.25 seconds. And then our computational time is 0.973 seconds. And so here are some physics principles that I used. So we used the PHYS law, which describes a magnetic field generated by a constant, which is given here, which is B equals epsilon naught over 4 pi. And then the charge times the drift speed times the r hat, all over r squared. And then the electric current, which is a Faraday's law, when the magnetic flux or the magnetic field changes with time, the electric motive force is produced. So it's shown on the right here. Then we also use F equals ma, and for every action there's an equal and opposite reaction, which is Newton's second and third law. So for our observed model, our initial conditions is the bar magnet and the stopwatch. And then our system would be the bar magnet and the aluminum tube. And its surroundings would be everything else. So this is what I got for our observed model. So for the magnet, we got a mass to be 0.026 kilograms. The mu of the magnet is 1.477. And then for the tube, we got a length of 0.3 meters, a width of 0.0065 meters, and then an inner radius of 0.024 meters and an outer radius of 0.0305 meters. So we ran 3 trials for this experiment. So for the first trial, we got a time of 1.24. Second trial, a time of 1.31. The third time, a time of 1.21, which gave us an average of 1.25. And so this is my goal script initial conditions, all right here, which includes my initial conditions from the previous slide. And so these are like the physics principles that I used. And so this is my computational model results. And so here are some similarities between models. So for the experiment time, it's 1.25 seconds. The computational time is 0.973 seconds. And then some assumptions we use is the bar magnet acts as a magnetic dipole to apply Bohr-Sparks law. And then there's negligible air resistance. And the only force involved are magnetic and gravitational. So here are some possible sources of error. So the electronic/magnetic devices and surroundings could have affected forces such as laptops and mobile devices. And then there could be a friction against the sides of the tube, which was not considered in the calculations. And also the stopwatch starting and ending may be inconsistent. So now for discussion. So what if the resistivity of the conductor was induced as close as possible to zero? How would the dynamics of the falling magnet change? So as we know, due to Ohm's law, the induced current in an aluminum tube would be much greater, which in turn creates a greater magnetic force on the magnet and could have counteract with the gravitational force, which prevents it from falling. And so what if holes or slots were cut into the tube? How would it affect the ring currents in your model? So the induced current in an aluminum tube would be less since the holes would disrupt the current and the magnet would fall through much quicker. So let me just go back to my glossary quote to just show you guys one more time. So here we are. And yeah, so we got our time in tube to be 0.73 seconds, which is somewhat similar to our experimental time. All right, thank you guys for listening. Goodbye.